morning. So it's a pleasure to introduce today Evanthia Hatziminaoglou from ISO. Many of you know her because she was a postdoc, her second postdoc here at the IC from 2003, 2006 in my group on Herschel Spire. But before that, she completed a PhD at the University of Toulouse on quasar formation and evolution and cosmological constraints. Then she moved to ISO for the first postdoc and worked on the ISO imaging survey. Then when she came here, we were involved in one of the first large surveys with Spitzer, Swire. She worked on that. She also worked on Herschel, preparation for Herschel, work on the Instrument Control Center, the group who developed the very successful Herschel pipeline that has been one of the reasons of the success of Herschel. And then in 2006, she moved to ISO, and she worked for several years at the virtual observatory, European Virtual Observatory facility at ISO as facility astronomer. In 2010, she moved to the ALMA Regional Center at ISO. That's what she's going to talk about today. I mean, what are her duties, her responsibilities in the ALMA Regional Center. She's the network coordinator of the European ALMA Regional Center. It's different from the other regional centers in the States or in Asia. At the end of the talk, she will introduce some of the tools that have been used very recently by some of you, maybe to prepare ALMA proposals, the ALMA Observing Tool, and also another tool that users of ALMA can use to follow the observations. I mean, how the observations are done, what is done, what is the status of the processing, etc. The message we want to give with this talk is that we are paying for this facility. This is the biggest facility on the planet. There is nothing like this. This is like the ELTs in the optical and in the infrared, but we don't have the ELTs. We have this. We are paying that. So use it. It's not so difficult. So I hope she can convince you better than I.
Well, thank you, Ismail. I think I just need one of those. Switch this off. So thank you very much. Thank you for joining this informative talk. So it is going to be an informative talk. There isn't much science here. I just want to convey the message Ismail just said. So ALMA is working now at full capacity, and it is very, very easy to use. So I don't know if you realize how easy it is to use, because the support you get is such that for people that have never heard of interferometry or millimeter, submillimetre, or whatever can use it, is really there for everybody. And this was one of the main initial goals of the project, and I think we have succeeded in doing so. As it's going to be an informative talk, I want you to interrupt and ask questions whenever things come up. It's mostly about the structure of ALMA as a virtual network, so in matters of support, but as well as a facility. There's very little science towards the very end, just for you to see what can be done with this fantastic instrument. So the reason I decided to give this talk is because I started preparing for my visit here right after the deadline. The deadline was on the 20th or 21st of April, I can't remember anymore. And then just before coming here, I checked the number of proposals that were submitted from the IAC, and it was very, 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 very low. It was like 2, or maybe even 1, I'm not sure. So I think it's a pity. It's a huge institute with a lot of potential, and again, I think you don't realize that the level of support you can get. You basically get reduced data at the end, so just apply for it. Okay, so let's start and let's see if I can convince you about the necessity and the usefulness of this. So a very, very generic, general introduction. So ALMA is a millimeter submillimeter telescope. It's located at the Chajnanto Plateau in the Atacama Desert in northern Chile, at the border with Bolivia. And it operates between 0.3 and almost 10 millimeters, so basically 30 to 950 gigahertz. The science goals are listed here. So these were the very high-level initial science goals, but of course, since the beginning, ALMA has been doing a lot more than just these things. I'm not going to read it. I think the talk is going to be available afterwards. You can go back and check whatever the details you want. Just want to bring up front the advances ALMA has brought to astronomy. So these are two examples of. So this is HL-tau. We're going to talk about it later on. This is a protoplanetary disk, and this is a gravitational lens. So this is the status of the observations before ALMA, and this is what ALMA did out of these things. So I think there is no arguing here. It has really revolutionized many of the fields of astronomy. So a bit of detail. So ALMA is basically 3 arrays. So there is the main array, which consists of 50 telescopes of 12-meter diameter. There is the Atacama compact array. So this is the smaller telescope of 7 meters that are sitting in the middle, around which the 12-meter antennas are expanding depending on the configuration. And the total power antennas that observe with individual dishes if you want to observe large structures. So here you can see this is the ACA, the compact array. It doesn't move, it always stays there in this configuration. These are the 4 PM antennas, so these are the total power antennas. And the rest is the 12-meter antennas that are moving from the very compact to the most extended configuration that can reach nowadays 16 kilometers between the longest baselines. So this is a different view of the same. Again, you can see the compact array there, and these are the bases. So on these bases, depending on the configuration, the antennas are being moved in specially made trucks, I want to call them. There are 2 of them made by ISO. So you put them on the truck, and little by little, they move them from one pad to the other, depending on the configuration you want to achieve. And of course, this is not done on daily basis, but it's done on sort of 3-week to monthly basis, where the configuration changes, because it takes a lot of effort and a lot of time to move the antennas. So the location, as I said, is somewhere here. It's in the Atacama Desert. You can see it's a completely desertic place. Bolivia is very nearby, so these mountains are already in Bolivia. Apex is sitting there as well, so this is Apex. So it's very nearby. So this is all at 5,000 meters. So there are people that are working there day in and day out. So they have to carry bottles of oxygen because it's very difficult to breathe and do other stuff at the same time. The OSF, where the operations are run, is at 2,900 meters. This is a much easier place to be. So all the operations are run remotely. So the telescopes are being monitored and the observations are executed from this place, the OSF. That hosts on a daily basis about 120 to 140 people. There's always a lot of people there, from astronomers and engineers, the personnel that's taking care of the place, and etc., etc. So these are some pretty pictures, again, of the same view, just to see the antennas, how they look like. This is the building that hosts the correlator. So the correlator is where all the signals of the antennas go there by cables, and then they're being combined and in this building with huge computers. And the ALMA correlator is by far the most powerful computer at such an altitude. And again, another view. I think the best thing is to go and see it yourself. It's really amazing up there. So as I was saying before, the top goal of ALMA was to give the possibility to every single one of us to do science. So as an instrument, it's a high resolution and sensitivity 3D instrument, so it gives you back cubes. All the observations are carried out in service mode, so there is no visiting mode, and the schedule is dynamic, so it takes into account the weather conditions and the priority of the projects and the requirements and everything, and then it almost decides what will be observed next. It has a complete end-to-end data flow system, so data go in from the telescope and then basically comes out reduced. The data that are delivered to the users are science quality data, images, basically calibrated and reduced. All this data, raw calibrated and image data, become available to the archive. The proprietary time is 1 year, and then they become public to everybody. You can just go to the archive and access all the data that was observed until delivered until a year ago. And last but not least, it has a very friendly and widespread user support structure through the ALMA Regional Centres, so in Europe, in East Asia, and in North America. Now, this slide a bit repeats the previous one, but I want to stress that this ALMA was conceived quite some time ago, but they had a very high-level science operation notions at the time, which they tried and did implement. So again, it's only service mode, so there won't be any visiting mode for the foreseeable future. I think it's just not possible. So you don't need to go there, although it's a pity because it's very nice, but you just send in your application, and then sometime later you'll get your data. The observations, since it is in these wavelengths, they are carried out 24/7. There are, of course, still some interruption for maintenance and COE activity, so EOC activity, so this extension, optimization of capability. So basically, this is the evolution of the, I'm having a senior moment here, commissioning. But still, the possibility to observe 24/7 is there. And right now, I think we're observing about 4 to 5 full days a week, with some breaks in the mornings or afternoons for some maintenance and technical works. So the observations, when you prepare your observations, what you prepare is your science goals. So basically, you give some high-level scientific requirements for what you want to observe, and these are then translated into what we call the scheduling blocks, that are files, XML files basically, that the system understands, and they go into the telescope, and the telescope generates the observations you required. And again, the default output is reduced, fully reduced, calibrated, and imaged data cube. So you can take them. Usually you will need to re-image, because the imaging depends a lot on your final scientific goal. But again, the images you get out are science ready in many respects. The JO, so the Joint ALMA Observatory, which is sitting in Chile, is responsible for the quality of the images of the data products. However, as I will mention later, the QA2, the quality assessment 2 level, which is basically the final reduction, is distributed nowadays at the ARCs. And again, all this ends up in the archive, and as you will see later when we'll talk about the publications, the archival research with ALMA is ramping up now. So there are more and more people using archival data to do their science. So the first thing I want to talk about is ALMA as a geographically distributed network. So this is very new in astronomy, and it's also not very common in business models still, even though one would think that now with the internet and stuff, one could be sitting anywhere and doing their work for whatever company or institute or things. But still, people have the need to see each other and work together. So this model is quite novel in a sense, especially in astronomy. It hasn't been tried before, and it actually works. So what is happening? So each executive has one ALMA Regional Center, which is responsible for the communication and the user support, the communication with the community. And there is one in each executive, so there is one in Europe, one in East Asia, and one in North America. And these ARCs, we call them, provide operational critical services to the ALMA operations in Chile and interact with the community. All this is done in close links with the Department of Science Operations, the DSO in Chile. And for whatever questions you have, whatever interactions you have, really your ARC, your local ARC, so in this case the European ARC, is your one-stop shop for all things you can think of. So this is a schematic just to show the level of interaction between the various things. So you have the Joint ALMA Observatory here. These are the 3 ARCs. The peculiarity of the European ARC is that the user support, or part of the user support, is provided by what we call the ARC nodes. These are groups inside the institutes that have experience in millimeters and millimetre and/or interferometry that are spread all over Europe. So we have let's see if I remember them all. So there is one in Iran that is responsible for Spain, France, and the Max Plancks. There is one in the UK. There is one in the Netherlands. There is one in Germany that takes care of the German universities. There is one in Czech Republic that takes care of the Czech Republic and the rest of East of Europe. There is a center of expertise in Portugal, and I will explain the difference between the two. And there is the Nordic one that is responsible for Northern Europe, well, for Scandinavia plus Denmark and the occasional other project. And not sure if I'm forgetting something, but we'll get back to this. So this is a bit peculiar with respect to the other arcs, because the other arcs are very centralized, especially the North American one is everybody sitting in Charlottesville and this is it. In East Asia, they little by little start developing a similar-like structure because they have accreted South Korea, they have accreted Taiwan, so these places are by default, very far apart from one another. So their model starts resembling a bit the European one, but not at the scale that we're doing things in Europe. So as I said, the arcs are the interface between the project and the community. And these ARC nodes, you have to realize that they are really there for you, for your support. So they are real experts, and their most important task is to provide face-to-face visits. And face-to-face visits can happen either to prepare your proposal, or to analyze your data, or to reproduce your data, or to help you do archival research or whatever. So you're not there alone. Even when you get your fully reduced data, you can still request to go for a visit to one of your local, usually, or any other ARC node, and they will help you do your science, basically. So this is how they, where they sit, how they look like. Yeah, sorry, I forgot Bologna before. So basically, this the ARC nodes, they made a request to become ARC nodes at the beginning of all this, apart from André Hov that came a bit later. And so these were mostly centers that have a lot of experience with millimeter, submillimetre astronomy and interferometry. Later on, André Hov joined in because the eastern part of Europe did not have any support at the time. And the last addition to the network is Lisbon. So this is not a full node yet, in the sense that they cannot provide face-to-face support for data reduction. However, they do still a lot of work. They're doing a lot of data analysis, they train their community, etc. And they are on the path of becoming, at some point, a full ARC node. So these are the high-level perspectives of the ARC network. So again, their role is to make ALMA accessible to all European astronomers, and they are contributing in more ways that you can ever imagine into making ALMA work, actually. It's a lot thanks to them, that to the European ARC network, to the nodes, basically. It's a lot thanks to them that ALMA works at the level it works and the success it has. So there are some basic concepts that all the scheme follows. So first of all, and you have to realize that this is quite important points, actually. So there are no contractual obligations. So that we have never signed. What was it? We never signed a contract with them. They don't have any, formal legal obligations to do what they're doing. Everything is based in goodwill, in trust, and in some memorandum of understanding that actually sets a bit, delineates the borders of this collaboration and let's say the limits of what can or cannot be done. Also regarding finances, ESO does not provide any financial support to the nodes. Each node goes to their own funding agencies, and they try to convince them that the work they're doing is important, and this is how they get funding to continue their work. And the funding schemes vary widely, so there are nodes that have to apply year after year to be able to continue their work. There are other nodes whose funding scheme allows them to apply for longer periods of time, 3 to 5 years, and they feel a bit more secure that they don't have this stress every year to prove that that things are working. However, so far there hasn't been any problem with anybody due to thanks to the big amount of work they're doing and the success that the network has in the eyes of the community. So also there is no guarantee time. There is no guarantee time for the executives. There is no guarantee time for the ARC nodes. Everybody's competing on equal footing. The observing time is just divided among the executives based on the financial contribution of each executive, and this is it. So everybody else is competing on equal footing. And as I mentioned before, this model is quite experimental, or started up being as something experimental. Now it's working. There is no reason to change it. But what makes it weird is all these conditions, because basically, seen from the outside, people usually ask, okay, so what's in it for them, or what's in it for us? But still, it's a collaboration that works, and we hope that this example can be used in the future for other facilities, such as the ELT, for example, or even now SKA has already started looking into a distributed network like this one. So if you're interested in seeing the details of this collaboration and how these things work and all that, we put in on the... well, that's supposed to be Messenger, December 2015. And it's an article describing actually the functioning of the network, the European ARC network. So the ALMA Regional Centres provide a set of services. This is a predefined set, and it was defined in the ALMA operations plan that was set out in 2007, so even before the beginning of operations. And these are divided in core functions and in additional functions. So the core functions are described here. So basically, this is scientific support services, so proposal preparation, observations, data quality assurance, archives, and of course we're providing also astronomer duty shifts. And also face-to-face support, this is part of the core functions. The additional functions include all these things, so it's community training, so there's community days usually before the call for proposal, where they prepare the community for the new capabilities of each cycle. There is support for special projects, if your project has some particular needs, support with archival data, and so on and so forth. And these tasks are divided between the core ARC at ESO and the ARC nodes in Europe, like that. So these staff are taken care of by ESO, and all these staff are taken care of by the ARC nodes. And the face-to-face support is a core function, this I stress, and this is basically the raison d'etre of the whole network of the nodes themselves, actually. This is the task they have to provide and that they do with all their heart. So there's also financial, oh my God, there's financial support by RadioNet. If you want to visit a node that does not have funding themselves, or you want to visit a node other than your local node, then you can request funding, and usually they cover accommodation and trips. So if you want to go and reduce your data or whatever, learn about things, there's possibility for funding. So this was how the things were set up in the operations plan before the operation started. In reality, things look a bit different. So the ARC nodes, in fact, do much more than what they were supposed to be doing. And these are the additional tasks that I've taken on. So first of all is quality assurance. So at the beginning, the pipeline was supposed to be ready well, when the operation started, and as is usually the case, this was not the case, so JO started doing manual calibration and manual imaging, and then they realized that there was so much data they couldn't, so this was distributed across the network in the ARCs. And in Europe, since we have all these people in the ARC network, they were very kind, actually, and accepted to do a part of the quality assurance. So now a lot of the quality assurance, you will see the number later, is done at the nodes, actually. So the nodes already know your project even before you go there to visit them. Contact scientist is something that was not foreseen at the beginning. So basically, whenever a project is accepted, a person from the network or from the project will follow your project throughout its lifetime. So as soon as it's accepted, you will get an email, a notification saying, you know, you've been assigned to this person, and this person will follow your project from the creation of the SBs down to the observations to data reduction, and later on, if you want to go and visit them and work with them in the analysis of the data set. So this was not foreseen. This is a lot of work for the ARC nodes, but they accepted it again. So this is what they're also doing. And then they get quite often involved in size verification, commission, extension, and optimization of capabilities, either by going to Chile or by doing stuff in their home institute, like reducing test data or whatever you can imagine. And they have also taken other various tasks or accept to do things as they come in. Sometimes we ask them to review documentation or I don't know what. But anyway, they're doing a lot of work. So this is the numbers I was talking about. So quality assurance, all this was supposed to be happening at the JO. The reality is this. So the blue is what is happening at ESO, and the rest is what's happening at the nodes. So about 65% of all QA2, so data reduction, is done currently at the nodes. And this is the breakdown by node. It's not really important. What is important is the total, and it's a lot of work. This is the contact scientist. So basically this gives you the distribution of projects in Europe. So in blue, it's the projects that nominally belong to the catchment area, let's say, of each of the nodes. In purple is the actual number of projects supported by each node. So you will see, for example, this is in cycle 4. IRAM had really a lot of the accepted projects, so about a third of the European projects fall into the catchment area of IRAM usually, so it's either Spanish, French, or a project from the Max Planck. And due to an understaffing reason at the time, they were not, they couldn't take care of all of them, so they were a bit redistributed across the network. And so you see some people, or all the other nodes have a bit more projects, support more projects than they normally have. This worked into fantastically. No quarrels. I mean, everybody's trying to help colleagues and the users to that. So anyway, everything went very smoothly. Please keep in mind that there is a 6 weeks, or in the new model that started in cycle 4, there is a 6-week delay between the announcement of the results. So if you're told that your project has been accepted at some point at the end of July, and you have until some point in September to prepare your observations. Now the observations are mostly prepared by the users, and with the help of your contact scientist if you want. And during these 6 weeks, this is where all the distribution of the project happens, the preparation, the submission to the archive, and all that. This year, the phase 2 deadline is in September 7. It's a week earlier compared to the last year, so keep this deadline in mind if you have accepted proposals. And finally, this is the number of people working in the nodes. So this is at ISO, we are about 15 people plus or minus, plus about 4 ISO fellows at any moment. Most of the people have mixed contracts, which means that we have a fraction of our time to do science and fraction of our time to do duty. So 1 people doesn't mean a full-time equivalent. It's usually half or maybe a bit more. So it sums up to about 10 FTE at ISO, and across the nodes, including staff, postdoc, IT, and everything, is 53 people, the equivalent of 21 FTE. So totally, we are a lot of people and a lot of FTE, but doing a lot of work as well. So if you ever had an accepted ALMA project, your contact scientist is for sure one of these happy people here. So we try to meet once per year face-to-face to discuss issues, problems, to get to know each other, because of course you understand there's a lot of movement in the network, so there are a lot of people that leave, there are a lot of people that come, because a large fraction of all these people are postdocs. So we meet once per year to solve problems. It's much easier to solve problems face-to-face rather by email. But anyway, we all appreciate these 3-day-long meetings, and everybody in the network thinks they are very useful and fruitful. Now let's see ALMA from the astronomical facility point of view. So far it was just a abstract notion of a distributed network. So these are the ALMA bands. Oops. These are the ALMA bands, as they are offered now in cycle 4 and 5. So all bands from 3 to 10 will be available in cycle 5. In cycle 4, band 5 was not available. So actually, the observations that are being carried out now, they do not offer band 5. Also, due to some front-end issues, band 5 will only be available from March on 2018, which means the middle of the cycle 5, which unfortunately excludes the long baselines, because cycle 5 will start with a long baseline configuration, extended configuration. But anyway, band 5 has become a reality and is being offered as of cycle 5. These are the cycle 4 and 5 capabilities for you to get an idea of what you can achieve. So the numbers in parentheses correspond to cycle 5, the others are cycle 4, so the current cycle. Cycle 5 deadline was, as I mentioned, in April, so you cannot apply anymore, but this is what will happen to your proposal if it gets accepted. So 40 antennas with the main array, 10 antennas with a compact array, and 3 TP antennas available in this cycle, and the corresponding numbers in parentheses for the next cycle. The bands we saw before. The angular resolution is not going to change much because we have already reached the longest, the most extended configuration, so you can achieve about 0.025 arcsecond resolution. New capabilities include single, dual, and full polarization in cycle 5 in bands 3, 6, 7, and 4, 5 in the next cycle. We're now offering ACA standalone observations in cycle 4. And actually there was a second call during cycle 4 that just is about to close, I think, again, that offers the possibility to apply for extra standalone ACA observations if you so wish. Large program was a novelty in the cycle 4, so these are projects that require more than 50 hours of observing time, and there are only few of them awarded because of course it's very difficult to schedule them because usually people want to observe their favorite Hubble field, for example, and then there's just not enough time to make the same observations. It was also a bit of experiment to want to see how it goes. Can we support such projects? How do we deal with the QA2, etc.? So it worked out fine. So in cycle 5 there will be more large programs than compared to cycle 4. There are also VLBI observations in bands 3 and 6 that are carried out in campaign mode. So the campaign for this cycle was in April. I've heard it was successful, but I don't think we're going to see any data before a very, very long time. So these are basically observations with combined with other telescopes around the world. And the last novelty of cycle 4, it will also be available in cycle 5, is solar observations. So ALMA is a huge solar telescope, apparently, because it managed to successfully observe the sun without burning. And the results, at least from the commissioning, were very, very interesting. I'll get back to that shortly. So this is the distribution of requested time as a function of array. And you will see this is really very inhomogeneous because people go and observe, apply for their favorite fields. This is for cosmology, of course, but I'm sure there are the same also for galactic astronomy. So by far the CDF South is the most popular field. Everybody wants to go and observe it. The Cosmos field comes second. Very close there is XMM, LSS, and other popular fields here. So if you want to increase your chances of success, try to propose for objects that fall here. Much easier. Because of course all this is taken into account when the panels are trying to make a list of the accepted projects. They have to take into account this. They cannot award all the time for the CDF, no matter how good all the proposals are. So this is something to keep in mind. So all this information and a lot more can be found in the ALMA Science portal here that is kept up to date. This is a new look and feel thing, which it doesn't look nice, right? It's terrible. Anyway. Anyway, well, so here you have a variety of news. There is ALMA news, there is local news, so from the EU ARC. Every time there's an announcement, it will appear here. There is some highlight of the latest scientific result. But also there's a lot of information, like for example the ALMA status page. So when you're a PI, a successful PI, you always wonder about these things. So we can't see what it is, but up there is the weather conditions at the AOS, so the high side, so you know if your project could be observed under the conditions or not. These are the latest observations that have passed QA0. So QA0 is the first check that we do at the telescope. So we observe NSB and we check whether it's more or less compliant to the requirement. If yes, then 0. It's passed, otherwise it fails. These are the latest public observations, publications, etc. And here there is a link to the configuration schedule that looks like that. So that gives you the configuration as a function of time. So you know when the configuration changes, and you also know when your project is eligible for observations, because each project has depending on the resolution you ask, has a range of configurations that can be observed, usually one, maybe one or two. So this gives you an idea of when to expect your project to be observed. Now I want to go into some ALMA highlights, because after all it is a telescope. And just for you to see the type of things that can be done in case you haven't already seen this thing. So this is Juno. Juno is an asteroid in the asteroid belt behind Mars, in a distance between 2 to 3 AU. And the light you see here is not reflected, it's not sunlight reflected, but it's actually Juno's own light that emits at these wavelengths, because it's very cold. It's like minus 110 degrees or so. So these are shots taken in different times, as you see, so you can actually observe the rotation of the object. This is HL Tau that we spoke before. So this protoplanetary disk at a distance of 450 light years is really nearby. And it's a very young star sitting in the middle. It's a star that is smaller than our sun. And actually these observations sort of revolutionized the field of planet formation. So this, the rings that you see here are thought to be generated by giant planets that are rotating around the star into the disk, and they are swiping the material around them. Now the thing is that this star is quite small, so you wouldn't expect, and quite young actually, so according to some theories at least, you don't expect giant planet creation around so young stars or around so small stars. So it brought a new insight into the planet formation. Furthermore, despite the size of the stars, so this is smaller compared to ours, the diameter of the protoplanetary disk is 3 times that of our solar system. So basically, this is the orbit of Pluto. So it's 3 times larger than that. So it's quite spectacular, in fact. This is well, this telephone number object. So it's a young stellar system. So again, it's in our neighborhood, more or less. It's very young. So and these are basically 3 stars that have been born in different time scales from the same material here. So this came sort of as a confirmation into some theories that want these systems to be born from the fragmentation of the disk of gas and dust that accumulates around young stars. And actually the youngest of this star is about 15,000 years, which, just to put it into context, is about where the time where the pig became domesticated. So it's really, really, really young. Another thing, this is a quite recent observation. These are not fireworks, actually, even though they pretty much look like it. So these are observations in the Orion molecular cloud that sits just behind the Orion Nebula. And so these are, oh, well, okay. So actually this is a birthplace of stars. So these stars were born, there's a lot of stars in there. They were born about 100,000 years ago, and they are moving. And then about 500 years ago, 2 of them just moved a bit too close to one another, and they just collided, and poof. So this is what we see here. And yeah, 500 years later, we can observe this amazing thing from the Earth. So this, of course, we're in our neighborhood. So this is at the other side of the universe, basically. So this is an Einstein ring, as you can imagine. And this was first observed by Herschel in the H-Atlas collaboration. And in Herschel, it was just a blob. And this is what ALMA made out of it. These are not the the largest resolution images. So basically, this is a galaxy that sits at about 12 billion light years from here. So it's the redshift 3 and a bit. Right in the line of sight, there is another galaxy at 4 billion light years away, which creates this phenomenon. So the light curves and generates the ring. So this is what ALMA made with the highest resolution. So this is really, really amazing, the details in which they can be studied. Now the nice thing is that, so this is the HST image of the lens. This is the ALMA images, and so a second analysis of the same data set showed this is indicative, it doesn't exist actually in the image, but showed the location of a dwarf galaxy at the same distance as the main lens, which is not visible, but because of the distortions it created, its existence and location could be speculated. And this is, of course, very important because these are the galaxies that might contain the mass we don't see, right? So speaking of highlights, so these are the first solar observations. This is from the science verification campaign that was carried out in December last year. Everything was very promising. Unfortunately, the science observations that took place, sorry, this happened a bit earlier. The science observations that took place in December were not very successful, not because of ALMA's fault, but because of a silly software issue that did not read basically the ephemeris file and went and observed for all the project the center of the sun. And that was quite unfortunate because the solar community was expecting a lot from this campaign. So I think the observations, some of them might be repeated, but it created a bit of discomfort, let's say, or unhappiness in the solar community. So in terms of numbers and publications and what happens to the data once they have been reduced and delivered to the people. So this is the publication rate, and the color marks the various categories. So disk planet formation, ISM and star formation, and active galaxies produce more or less the same amount of publications, and they're followed closely by galaxy evolution and then stars and stellar evolution, cosmology, and the rest is just ramping up now. This plot was made, I think, on February 2017, and this is why you observe the drop here. In reality, it's going to shoot much higher. And of course, since the plot was made, the number went up by almost 100. So we've reached about 670 ALMA-based publications now. This is broken down into PI, archival, and PI plus archival papers. So you see already the archival science is also ramping up. And this is the time of publication, the fraction of ALMA data published, so into refereed journals, as a function of the time that they became available to the PI. So there is a 1-year proprietary time during which the PI is the only one that the PI and the collaborators are the only ones that have access to the data, then they become public. And this is how data are being published. So basically after a number of years, all the data are used to do science. And this is the publication rate as compared to other facilities, so we're following very closely that of the VLT. And the last highlight, which is not scientifically purely speaking, but is quite important for the people that go to the mountain quite often, and for us that go there to provide support, is the ALMA residence. So this was the last deliverable of ISO. It has been now handed over in the second half of April. And it's fantastic, especially if you compare it to the containers we used to sleep in until now. Though I must admit that I'm going to miss them. They were quite cozy, and so you can do like that and you can touch the walls of your room. It's quite impressive. So I think I'm going to stop now, and I'm going to take your questions for whatever you want to discuss or... Sure.
Are there any questions? No questions? Okay.
I wanted to ask if there is any support for people who want to use archival data only.
Yes.
It's the same as if you are a PI.
You can request a visit, a face-to-face visit. So there's a full system. So to do it formally, you have to go through the ALMA help desk. And there is a special category to request face-to-face visits, and then depending on where you come from, you will be assigned to a node. If you want to go to a specific node other than your own, this is also possible. There is also funding for that. And then you request an archival research support, and you take it from there. But there is no difference between this and PI data.
Thank you.
Any other questions?
Can one ask for support from a different node? I mean, our logical node, I mean, official node is IRAM, no? Yes. Grenoble. But they are also quite busy with NOEMA, etc. So can we ask to go to Manchester or to go to Garching? Yeah?
Yeah, Garching doesn't provide face-to-face support. The support is exclusively done at the ARCs, but you can ask for support from any nodes.
Any other nodes? Yeah. Okay. Yeah. Thank you.
Okay. Is there Evanthia?
Do you know what is the astrometric accuracy of ALMA?
The astrometric?
Accuracy.
Well, an exact number, I don't know, but it's very, 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 very accurate. I don't have the number in head, but you can find it on the ALMA documentation. They are on the science portal.
Is there any other question? No? Okay, so if not, let's thank Evanthia again. And I think there is coffee in the library now.
Well, the thing is the following. So, as Ismail said, I'm willing to show you how to prepare proposals and or follow your project. Now, the question is, do we do it now, here in this setting, or maybe in a smaller room some other day with those of you that really want to know? We can also have, some interaction rather than me sitting here and showing, I don't know. If there is real interest, I'm very willing to do it.
Right now?
Well, now or any other day. So, it's up, yeah, as you wish. fine. Yeah. Okay. Yes? Okay. Yeah, yeah, yeah. No, I think, no, stop it. I mean, it's just, you can stop it, there is no point now.
No, just in case
That's fine. Okay, so as a PI, you will be confronted to two tools. So one, you will use it if you want to apply for ALMA data, and later on, if you're successful, to create USBs. And the second one is once your USBs have been created, you can follow the evolution of your project as it being observed, reduced, etc. So the first one is the ALMA Observing Tool. So there is a new version for every cycle. So I'm going to open the cycle 5, with which the proposals were prepared for the last call of proposals that closed a couple of weeks ago. So this comes in two flavors. It's a web start, or there is an application you can download, and it's usually best to use the web start, because whenever there is an update, it's automatically updated. You don't have to worry about things. And in case you were wondering, it's a Java application. And when you're plugged, it doesn't take as long as that. So the first thing it will ask you is whether you want to generate a new proposal, or you want to load a proposal you were working with from your disk, or if you want to retrieve something from the Science Archive. So of course, from the Science Archive, you can only retrieve your own proposals, no other people's proposals. So here we are going to create a new proposal. Is the resolution good enough? Can you read? Let me check if I can change it. Where is it? This place. Where does it change? Yeah. No, that was not much better. Is it? Okay. So that's how the OT looks like. So here is the project tree that will be developing as you create your proposal, and here's the various things like the spectral information, the imaging information, the calibration you want to do, the science justification. All this will appear here in different panes. So here you have to fill in your title and your abstract. You have to select categories and keywords to add your name as a PI and your favorite Co-Is. And then what you do is you generate new phase 1. So this is phase 1 still before submission, science goal. And this is the structure of your science goal. So this is just a general description. You may want to fill or not. It's not important. The field setup is, of course, much more important. Here, this is where you provide the information about your targets, coordinates, velocity, redshift, etc., as well as your expected properties, so the continuum or line fluxes, polarization, line width, etc. This is the spectral setup. This is the window in which you're going to work when you want to define your observations. So if you want to do continuum or if you want to observe lines. The calibration setup is best to leave untouched. So the normal thing is that the observatory takes care of the calibration. If for whatever reason your observations require some specific type of calibration, or you want to do it your way, then this is the place to indicate it. And here you get information about you include information about your sensitivity, the largest angular scale that will define whether you need only the 12-meter array or if you also need the ACA or TP. So depending on the largest angular, the largest structure you want to observe. And there's also where you put your time constraints in case you're doing, I don't know, whatever project that requires specific time constraints or multiple visits, etc. And finally, this is the technical justification where you have to explain why you chose your sensitivity, why you want to do the imaging you want it, why you chose this correlator or configuration. So this information until cycle 3 used to go into the proposal, but in the end, to allow for more science discussion into the proposal, this became a section of the in the OT. So all this information now goes here, and it becomes, of course, available to the assessors. So the actual the science justification is appended to this. It's inserted into the system in the where is it? At the proposal level. So you attach it here. And at the end of the submission, the file that will be generated is a PDF that will include your science justification as well as all the information you included in the whole proposal. So let's see. Let's go for just a random object. So you put your favorite object, you resolve it. So it usually works. You should be careful for it, because sometimes you have to double check your coordinates because it's not always exactly accurate what comes from SIMBAD. And actually, a lot of the change requests we get after proposal acceptance is because of the coordinates were not really accurate. They vary by a bit, but anyway. So the object has been resolved. So here you can put your expected properties. If you want to observe continuum, you're going to fill in here. If you want to observe a line, you want to put the peak line flags here. So let's say we want to observe, I don't know. Okay, let's do something easy. Let's observe band 7 continuum, let's say, and we expect, based on previous observations or simulations or whatever, that the peak flux is, I don't know, like, yeah, okay, 1 millijansky. Since it's continuum and we will not observe lines, we don't care about the rest. And we're going to make just one exposure, so we go to the one pointing. And so we want to go to the spectral setup and set our observations. So if you just want to do single continuum, it does it for you. You don't even have to enter the frequencies yourself. Just click on single continuum, and this is taken care for you. Well, maybe you have to specify. Okay, the frequency. So by default, it selects the band 3. Otherwise, you have to change it here. Oops. And you get the automatic setup with the 2 sidebands. So these are the basebands. There are 4 basebands. 2 of each are into 2 sidebands. So the lower and the higher sideband. And here you really don't have to do anything else. The system is taking care of everything for you. You just see if the resolution you want is more or less the same. If you want to observe continuum, it doesn't matter. You just take the lowest one. You don't touch the calibration because this is it. In the control and performance, you want to put what resolution you want. We take 1 arc second. And the largest angular scale, depending on what it is that you want to observe. And you want the sensitivity per pointing of, let's say, that. Of course, you won't put the numbers like that. You have to think about them. No? I just want to make the thing work now. And this will give you the, oops. What did I do? Of course, if you do something silly, it will tell you, like just like I did now. So what was the problem? Configuration, check the SARing resolution within the regional configuration. SARing resolution. Resolution. What did I ask for? Why? What's wrong with this? Okay. So now it works, and this tells you that the total time for this observation, including calibration, is 2.5 hours. This is a very small and easy project. Here you have to break down into the actual time on source plus the calibration. And this is it. So because of the information I entered, this also requires ACA and total power array, because I asked to observe a structure that is quite large, that will otherwise be resolved by the main array. And here I have to justify in a few words why I have chosen the values I have chosen. So let's just for it to compile. Okay. So if everything goes well, you have to validate here. This is the little button. And here it will tell you everything you did wrong. So I didn't put PIs, I didn't put Co-Is, I haven't attached my science case, I haven't defined my type of proposal, keywords and all that. But once you fix all this at the proposal level, so all the errors came from here. So this is a regular proposal. I want to do galaxies and active galactic nuclei. I select 2 keywords, and then I put the names of PIs and Co-Is. Then you will get a green tick mark that will tell you no problem found. And then if you're confident that this is really what you want to observe, you go here, you submit your project, and this is it. So this is really, really, really easy. I mean, of course, you have to get a bit accustomed to the layout of the tool, but it really doesn't require much to do it. If you want to set up line observations, also you get a pop-up that will show you all the lines in the band you have chosen. Then you can select, the transitions you want and everything. It's really made for people that are not experts in this. Again, we can, if you really want to go into the details, we can set up another meeting and discuss it. The other tool is called SnooPI. It stands for Snooping Project Interface. So it allows you to follow your projects. Hello. And nothing happens. Cool. Let me see if I have another window somewhere. Ah, there it is. So if you go to if you connect to SnooPI using the same credentials you use to connect to the OT, to the science portal and everything, I'm having problems with the network, it seems. Okay. So this is the front page. So basically you see how many projects you have as PI, as Co-I, how many SBs as PI, as Co-I, your delegated projects. And down here you have information, or my projects don't have any news, but you'll get the latest news regarding, my SB number blah has been observed, or my SB is waiting reduction, etc. It has been delivered. So it's a quite modern interface compared to what was previously available. That was the project tracker that was really a bit too complicated for use. And SnooPI makes a distinction between active and non-active projects. So non-active projects are the projects that belong to a different cycle that have been already delivered and all that. Active projects are the projects that are still being worked on, either observed or being reduced. Here I'm connected to some test database, and this is why we don't see many projects. But basically the structure is this. So you can see in a glance the status of your project. So each of these symbols here means something. So these are rejected projects. This is a partially completed project. And this is a project that was approved but for which SBs were never created for whatever reason. And this little cube here indicates that there are SBs that have been generated and they are there available. You click it, you can see the list of the SBs, and by clicking on the SB, you go directly to the information of your SB. Now the view is a bit scrambled because it's okay. There you go. So here you get various pieces of information about the status. So this tick mark means that all the data have been taken. You have the information about which array has been used, array deck of your target, the band, representative frequency, etc., the number of successful executions compared to the number of executions required. The QA2 status, this means semi-pass, so maybe there are some data that are useful, but they did not really reach the RMS requirements of the PI. And here, clicking, you will get the full QA2 report. And below, you have the breakdown into EB, so execution blocks, because this has been required for execution, so each execution block has its own information that is being deployed at the bottom. Okay, all this in reality is much faster. So this is now a combination of network and the fact that I'm connecting to a test database, so that makes the whole thing so slow. And all these symbols have a meaning that you can get by hovering over. So this means that your data set has been delivered, etc. So here is the information on your on the B you chose with the system temperature, the number of antennas used, and other information. And here is all the information about the targets you have used. So the primary target, which is your science target, as well as all the targets that were used as calibrators to calibrate the atmosphere, flags, phase pointing, bandpass, etc., along with their coordinates and the time spent on each of the sources. So basically this is it. So as soon as there is one EB execution block for which the QA is 0, so the first test says that it's a pass, you will get here the possibility to fire directly an archive query. So this will launch the archive query for this particular EB into the ISO archive. It will return something that doesn't look like that. No. Well, okay, sorry, that's the usual demo effect. But anyway, you will get a return, the usual archive query output return, where there you can directly view the PI, you can directly select what you want to be to download, and etc. So the same goes for SB. So instead of listing your project, you can list your SBs. All these tables are of course sortable by a variety of parameters, and again you have a quick look of the status of your SBs. They can be partially observed, fully observed, so some data, no data, some data, all data. They can be timed out because they require the configuration that has passed, or maybe they are cancelled because they were observed in some other cycle, etc. The manual is linked from here. There are links to Sign Portal, Archiver Query, and the help desk, and basically this is a small self-contained thing that will allow you to follow your projects once they've been accepted. So again, for more details, it's best we sit together and discuss. Yeah, sure. Any questions? So each executive holds a copy of the archive. So all the archives hold the same things, but depending on where you're sitting, you're redirected to your closest place for download. At ISO, yes. Yeah.
Okay, so any other questions? No? Okay, so I think we are done. Okay, thank you, Evanthia.
You're welcome.
2 segundos.